Hello, everybody. I'm very glad to announce and chair this seminar, this astrophysics seminar, and I'm more than happy to present the speaker, Juan Diego Soler, that he kindly agreed to give a talk today. So Juan Diego graduated in Universidad de los Andes in Bogotá, in Colombia, in 2004, and then he started a brilliant career, I would say, in astrophysics with a PhD at the University of Toronto in 2013, and following with two postdocs, one in Paris at the Institut d'Astrophysique Spatiale, in 2000, following that, essentially, and then afterward at MPIA in Heidelberg. Currently, is in Rome and started another postdoc at the Istituto di Astrofisica e Planetologia, and in his working, you'll see in the talk, in his specialties, is essentially involved mainly his activity on interstellar magnetic fields, and lately, while he was at Heidelberg, he was in charge in this research where they identified the Magdalena, the so-called Magdalena filament, galactic filament. So we will hear about this more in detail. Juan Diego is also a great divulgator, so he's really involved in outreach, and not only contributed in newspapers in El Espectador and El Tiempo, and also he written in November 2021 is written a book, essentially in outreaching essentially the cosmology. The title is Relatos del Clima. Yeah, we are looking forward to see the translation either in English or in Italian. I think I can read also the Spanish version though. So I think the stage is yours, and yeah, Juan Diego, take it away. Thanks.
Well, Giuseppe, thanks very much for this kind introduction, and thank you all for being in the audience today. I'm really sorry I cannot physically be with you guys today, but hopefully this is going to be a great talk. So yeah, so this is the presentation. Of course, it's not only my work, but also the work of many people, mainly the THOR collaboration and the Echogal collaboration. Some of them are based in Rome. They're shown in blue. So I'm going to be talking about mostly atomic hydrogen emission. And what are we learning from that? What are the perspectives of that work? And how that particular observation reveals a lot of details about the cycle of energy and matter in the interstellar medium. So let's just begin. This is an image of the sun this morning or yesterday. This is the most up-to-date image from SOHO. You know, the sun is the main source of energy for the planet Earth and probably the most important object of astrophysical research. And the sun is made mostly out of hydrogen. So it's been almost 100 years since we know that most of the atoms in the sun are hydrogen. Actually, 92% of those atoms are hydrogen, with only traces of other elements. And this is true for many stars. Many stars are like that, are mostly composed of hydrogen that gravitationally collapses and starts making nuclear reactions in its nuclei and produce nuclear energy. So if you want to tell the story of how you produce a star like the sun or a planet like the Earth, in which forms of life like us live, you have to tell the story of hydrogen. It's as simple as that. But the history of hydrogen is quite complicated. So this is the diagram of the state-of-the-art knowledge about the cycle of the life cycle of hydrogen in the interstellar medium. It goes from clouds of mostly atomic neutral gas that are at a characteristic density of around 1 particle per cubic centimeter, and they turn into stars. Just as a reference, the density in the middle of the sun is around 10 to the 25 particles per cubic centimeter. So we're talking about a story that spans over 25 orders of magnitude in density, and many orders of magnitude in size and in temperatures. And so it's the story of the change of phase of that gas that is very interesting. So I'm going to tell you a little bit about how do we came to learn about this cycle that takes the atomic gas and turns it into molecular gas that is colder and can collapse to form new stars. Those stars then die and release some of their material back into the interstellar medium. Some of it is ionized, some of it is neutral. I'm going to tell you about how we construct that story, and I'm going to tell you a little bit about what we know about atomic hydrogen and how we came to learn that and why it's interesting precisely in this moment in astrophysics. Okay, so let's not stand in ceremony, and I'll show you pretty images. So this is how the atomic hydrogen clouds in the Milky Way look like. These are the result of high resolution observation combining many observatories. But before that, let's take a step back to where it all began. So it all begins with radio astronomy. So Karl Jansky is the father of radio astronomy. No wonder he has a unit with his name. And here we can see him with this antenna with which he was studying the sky, the emission from the sky at 20 megahertz. So if you see those wheels that he uses to move his antenna back and forth, those are 41 wheels. They are the wheels of the first car. And he used this antenna and pointed at the sky in different directions to observe for the first time radio waves coming from the sky. With the headline in the New York Times in 1933 was "New waves trace the center of the Milky Way," because, as we'll hear tomorrow in the press release, there's always big news about the galactic center. It's also a very, very powerful source of radio emission of radio waves. The field was quiet for a really long time after this discovery by Jansky. And actually it was picked up by an amateur astronomer, Groth Reber, who built himself this antenna. So this is the Reber antenna that is a patrimony site in the United States. And he used this to observe the sky in 3300, 900, and 160 megahertz. So he made maps of the sky, maps of the galactic plane, but this was mostly the work of an amateur astronomer. Of course, these are the basis of what we know now as radio astronomy. But radio observations didn't come up in line until after the Second War. But during the Second War, something happened. This picture is a picture of the people in the Leiden Observatory in the Netherlands. And there in the circles, you see three of the most famous astronomers of the 20th century. Jan Oort does not need a presentation, but you know, he named the outer skirts of our solar system, but also was one of the first ones to describe the dynamics of our galaxy, the rotation of our galaxy. Then there's Marcel Minerd, that is he's a chemist, and he was specialized in the structure of molecules and atoms. And then there's Hendrik van der Holst, that was a grad student at this time. So together, these three people worked during 1941, while the Netherlands was under Nazi occupation, to figure out the transition of neutral hydrogen. So the neutral hydrogen, you know, is just a proton and an electron. And when that proton and electron, each of them has a spin, when those spins are aligned and there is a transition in which the spin is flipped, there's an emission. It's a forbidden hyperfine transition that emits light at 21 centimeters wavelength. This was the prediction. Actually, this granted Van der Holst his PhD, and it's an emission that is located in the range of radio waves. So where are the radio waves there? There's the diagram of the electromagnetic spectrum. So we see the visible light towards the center of this light. In red there, we see the hyperfine structure emission of the atomic hydrogen. This was not observed until later, in 1951, for the first time, using this box antenna at the Harvard University. Harold Ewan and Edward Purcell measured for the first time the emission of atomic hydrogen coming from the sky, coming from the galactic plane. Of course, these were very low resolution observations because, as you know, resolution depends on the wavelength. So 21 centimeters is a very long wavelength. You need a very big telescope to get very high resolution, but they didn't need that. They just needed to observe it for the first time. Later in Europe, the Dutch teams and the teams in Leiden started to refurbish these antennas. These are Würzburg radar antennas. So these are the antennas that were placed by the Nazi Germany army in the northern coast of Europe to detect aircraft that were coming from England, from the UK. So these antennas were refurbished. The receiver was changed. Instead of using radar, they were used to measure H1 coming from the sky. And of course, you all know the Milky Way, but just a small reminder, you can see it from everywhere in the world, is the band of the sky and is basically the edge of this disk in which we are living. And if you see it in the 21 centimeters emission, this is what you see. So what you see there is a diagram that has two axes. The first axis, the x-axis, is galactic longitude. So this is the orientation. This is the dimension that goes on the plane of the galaxy. So on the direction of that band of the sky that we see that we saw in the previous slide. So galactic longitude is just going along that line. Radial velocity is just the Doppler shift of the 21 centimeter emission line. So the 21 centimeter emission line has that wavelength at rest, but when you observe it towards the sky, you see that that line is shifted, and depending on the galactic longitude, is positively shifted, so it's moving towards us or it's moving away from us with a characteristic velocity of around 100 kilometers per second. What you're seeing there is the rotation of the Milky Way. So this was a secondary observation of the rotation of the Milky Way just after Jan Oort's observations of massive stars. So you're seeing there the Milky Way rotating. So this is from 1954, and something that you can do with this diagram is assume circular motions. If you assume that we're just going in a merry-go-round around the galactic center, and you compute the position of the sun at 8 kiloparsecs from the galactic center, and assume that this is the main source of motions, you can produce a face-on view of the Milky Way. And this is what they did in 1958. So this is the same team, still Oort involved, Westerhout and Kerr. And here you can see some features that look like arms. So this is the first observation of those features that we call spiral arms. Of course, it's very difficult because this assumption of circular motions is very broad. We know that it's not only circular motions that dominate these clouds of gas that we see towards the galactic plane, but this is the first face-on view of the Milky Way as seen by the gas emission. So this is very interesting, it's very cool, but remember that I told you that you need pretty big telescopes to go a little bit further. Well, that is the state of the art. So if you make a map of the galactic plane using the largest single dish telescope, for example, the Effersberg 100-meter telescope, you get a resolution of around 10 arc minutes. So if you take a band of the sky, it looks pretty blurry. So this is far away from the resolution that you achieve in visible wavelengths. So you need a bigger telescope. Of course, you can use Arecibo. With Arecibo, we were used to 4 arc minute resolution. But if you want to go further than Arecibo and the 300-meter dish that it had, you need an interferometer. So that's what was achieved with the Jansky Very Large Array in Socorro, New Mexico, where instead of building a monolithic telescope to capture the 21 centimeter line, you mimic a larger dish using this array of 17 antennas. And that was achieved for the first time in 2006. This is the result of the VGPS survey, where they got 1 arc minute resolution. So of course, this is for a compact array. The more distributed the antennas, the larger is the telescope that you can mimic with the combination of those antennas. So of course, we tried to go ahead and do a map with higher resolution. So that was the THOR project led by Henrik Beuter at the MPIA, in which I was working during the last 4 years. And basically, we used a more extended configuration of the VLA to produce what is so far the most detailed map of atomic hydrogen emission towards the plane of the Milky Way. So how does that look? So now it's time for a movie. This is the whole sky there, as seen by Gaia. What you're seeing there is just binning of emission from stars. And there we go into the galactic plane. So of course we didn't cover the whole galactic plane because we cannot see it from the northern hemisphere, and it's also too expensive. So we just cover a region of 50 degrees in the northern galactic plane. And what you're seeing there is the emission from atomic hydrogen. So there you'll see many features. So for example, you see those dots. Those dots are strong radio continuum sources. Most of them are galaxies that are behind the Milky Way that we can see all the way through because their radio emission is so intense that we cannot really separate it from the H1 emission. Then you see many filaments. Then you see some of the features of the interferometer up there in the upper edge of the image. You also see some shadows. Some of those shadows are H2 regions in our own galaxy that look very bright in radio continuum, so also they're hard to subtract from the H1 emission. And you also see some shadows. That shadow is a supernova remnant, that's W44. And you see other fainter shadows. Those fainter shadows are just the interaction of the different phases of the H1, as I'll tell you in a minute. Okay, so remember that story that I told you about making a face-on view of the Milky Way, just assuming rotational motions? Well, we did the same. We took our H1 observations and we did the LB diagram. Remember, the x-axis is the direction along the galactic plane, and the velocity is just the Doppler shift of the 21 centimeter line. And this is what we saw. We saw this accumulation of emission towards the particular features that we know as spiral arms. These spiral arms are determined independently using masers and other tracers, but we see that there's more or less a concentration of emission towards those sites, and we can construct this image of the Milky Way. This is the face-on view of the Milky Way emission. There you can see that the outer arm seems to be a little bit displaced with respect to the position that you get in other tracers. You also see some features towards the position of the sun. It's still hard to get rid of that of the features that are produced by the assumption that there's only circular motions. But this is pretty cool. This is a face-on view of a big chunk of the first galactic quadrant. So what I devoted myself to was a different dimension of the data, and is how does it look in the plane of the sky? So how does it look? It's full of filaments, of wispy things. You see some of them are very wispy, some of them are more puffy. So I try to identify which physics are behind all of these features and try to quantify that in general. Looking at the THOR data is very hard because it's just a lot of data. So if you take a 2 by 2 degree tile of the THOR data in one particular velocity channel, and you stare at it for 1 second, it would take you 8 hours to go over the whole data. So this is not something that you can do by eye. It's untractable, it's very difficult. So what I proposed to do was just using machine vision. So a technique to characterize a particular feature. So in particular, I wanted to identify sticks, or like those filaments, or that wispiness that the image has, and then compare that to a family of models of the Milky Way, in particular, well, numerical models of the physics of the Milky Way, and then see if we can learn anything from that characteristic. Of course, this is not a linear process. No, there are 1,000 characteristics that you can identify in an image. We try the filamentary structure, but there are many other things that you can do. Many of them we tried and failed, and this one is the happy story. So let me tell you how I identify filaments in the THOR data. So every time that you have a scalar field, you can identify the curvature of that field using the Hessian matrix. So the Hessian matrix is constructed with the second order spatial derivatives of that scalar field. So if you put together those terms of the Hessian matrix, you can actually identify what is the topology of that two-dimensional field. And in particular, when you calculate the eigenvalues, you can estimate where are the ridges of that topology, or what we would see with our eyes as filaments, as sticks, as elongated places, because it's the place where you have a lot of change in the derivatives in one direction and less in the other direction. That is what is identified as a ridge or a filament in an image. So let's not stick to the maths, but look at the image. So this is the image of just intensity. These are different velocity channels for the same portion of the sky. And in each one of the panels, you see different velocity channels in different colors. And now let's turn it into sticks using the Hessian matrix. So I'm going to just go back and forth so you guys can identify your favorite filaments and see that the Hessian matrix is just a way of describing that image in terms of structures which have a high value of this eigenvalue of the Hessian matrix, or that are characterized by being just elongated. Okay, so once we identify those structures that are elongated, we went ahead and characterized them. So on the left-hand side panel, you see the emission map for one 2 by 2 degree tile, actually two of them in the top and the bottom. In the middle, you're seeing the negative eigenvalue of the Hessian matrix. That is the one that identifies filamentarily. Filamentarity, if that's such a word. So the more negative that value, the more filamentary the structure is. So we can apply a threshold on that eigenvalue, and we get those sticks that you guys are seeing there. You see that they're not necessarily straight. And what you see as a gray shadow there, that is noise of the interferometer. Remember that we did this by combining single dish and two configurations of the VLA. And you cannot trick nature. You don't have a single dish telescope, so you're going to introduce some artifacts in the image just by the fact that your coverage of the UV plane of the Fourier transform of the sky is going to be imperfect. So you're going to generate some artifacts. Those are the things that you see in gray. So part of the difficulty of this test, of this work, was testing that indeed we're not just seeing the noise of the interferometer. So I hope I convinced you with this image that this is not the noise of the interferometer. And then in the last panel, in the right-hand side panel, you see the orientation of the filaments. You see that some of them are horizontal, some of them are vertical, and you're just reducing the dimensionality of the map. You go from a map of emission into a map of sticks and a map of angles. But still, that makes it hard to treat all of the data at the same time. Of course, you can do a histogram. This is a histogram of the orientation of those filaments for a particular tile. Again, for a 2 by 2 degree tile of the data, you see that it's peaked around 0. So the filaments are mostly parallel to the galactic plane, but we're still not learning that much from that. I mean, this is just 3 channels and the noise. So it's not that we're reducing a lot the dimensionality of the problem. So what I proposed to do was, in the same way that you can do a spectrum, you can average the emission, you can also do a spectrum of the orientation of the filaments. So if in the top you see the mean emission for that line, for the 21 centimeter line across different velocity channels, in the bottom you're seeing the orientation of the filaments. So there you can see that most of the filaments actually have orientations that are mostly 0 degrees, so they're mostly parallel to the galactic plane. But this is tricky because this doesn't tell you this is not an optimal estimator of the orientation. Why? Because the orientation of filaments is a wrapped distribution. Actually, if you just stretch a Gaussian over a circle, you can artificially generate significance. So people know that, and the people that know that are the people of condensed matter physics, or the people that work with random walk interpretation. So if you imagine that you have a random walk and you have unitary steps in a complex plane, if you have a preferred orientation, for example, if all of the filaments were parallel, you would have a preferred direction in the displacements in the random walk. So if you turn all of the angles of the filaments into orientations in a random walk, then you would see that the random walk goes in the same direction. If the filaments were randomly oriented, then you would see no displacement in that random walk in the complex plane. Of course, reality is something in between. It's not just preferential, but also a little bit of randomness in the walk. So the way to quantify that is this number. This is called the projected Radial statistic, and is the optimal estimator of a preferential orientation. So basically, this tells you the significance of a preferential orientation. So it's like a sigma. So here is the same spectrum that I was showing you before. So remember the spectrum of angles. Now this is the spectrum of the projected radial statistic, and what this is telling you is that you have up to 10 sigma significance for a preferential orientation parallel to the galactic plane. Of course, you may think that sigma cannot be negative, but it's just because I'm using a trick. Just by this definition, look that I multiply by 2 the angle. That means that I just have a second preferred orientation, which is 90 degrees, so perpendicular to the galactic plane, that would correspond to the negative sigmas. So positive means the significance in with respect to being parallel, and negative means preferential orientation perpendicular to the galactic plane. So now we can come back to this plot. Remember, this is the LB diagram. In the x direction is the orientation on the galactic plane. In the vertical direction, you're seeing just different velocity channels. And if you plot the angles, you see that most of the diagram is purple, so mostly 0 degrees. And with 2 exceptions, there are 2 big islands there of yellow, which are filaments that are perpendicular. And if you do the significance, we have up to 40 up to 40 sigma prefer orientation parallel to the galactic plane. Remember, here we only had 10 in this diagram because it was just one tile. This is for the whole data. And there are places where the filaments are just very oriented parallel to the galactic plane. So how do those filaments look like? Well, they look like this. It doesn't mean that you just have horizontal structures. That is not the case. Actually, you have a whole distribution. But when you add all of these little line segments, most of them are parallel to the galactic plane. And I think I don't need to convince you that that is the case in this image, despite the fact that you have some vertical structures. Out of those horizontal structures, which are very interesting, there was one that was particularly strange. So is this one. This is a place of the galactic plane where actually the bulk of the emission is above galactic latitude of 0. So the mean plane of the galaxy here goes up because the galaxy is not a plane. It's been well known for around 30 years that the galaxy is not flat as a disk, but it's more like a potato chip. So it's warped as a hat. And in this particular place, that warp goes in the vertical direction. So you can see it there in the image. In the top, you see that most of the emission is actually getting off the diagram, is around galactic latitude of +1. But there's this little guy down there, and that was weird. So that weird guy is coherent in emission. Actually, it corresponds to emission around minus 56 kilometers per second, and this is pretty long. This velocity would locate this object at 17 kiloparsecs from the sun. So this is really far. Graduate student Jonas Seid, currently at Heidelberg and looking for a postdoc, identified this object and started to do a study of the spectrum. So he did Gaussian decomposition of the spectrum and found the mean velocity of this ridge. And he found that this object also is compatible with a place in which the spectrum is very narrow. So this is an object that is cold, because in this case the width of the line is determined by the spin temperature of the hydrogen. And well, he saw there in the bottom panel that actually corresponds to this purple emission. Of course, you cannot always disentangle that. If you have a broad component and a narrow component, it's hard to disentangle it. But this is a coherent object that is at 17 kiloparsecs from the sun. So let's not get tangled with words, and let's go to a movie. So Jonas made this movie. So this is an artist's rendition of how the Milky Way looks like. That object would be located at the other side of the galaxy, all the way there. So if you want to see it again in the plane of the sky view, there is Magdalena. So of course we needed to put a name. Since I discovered with the machine vision technique of the Hessian matrix, I had dibs for calling it, and I call it Magdalena in the name of the longest river in Colombia. That is probably the most important river in my country. So how can you produce something like that is so bright and is below the galactic plane? The executive answer is we don't know. Basically because it's hard to produce something that is off the plane and very horizontal. But it's relatively easy to produce very horizontal objects as we learned from numerical simulations. So these are numerical simulations made with the ARIPO code. This is the work of Rowan Smith at the University of Manchester. And what she does is she produces a simulation of galactic potential and some spiral arms. And just by shear, by the differential rotation in the gas, you produce very elongated structures. So this is a simulation that doesn't have stellar feedback, so you naturally produce really long objects just by rotation. So this is promising. It doesn't explain Magdalena, but it's pretty cool. So let me make a summary of this so far. So we have filament orientation. Most of those filaments appear to be parallel to the galactic plane. There are some places in which the filaments appear to be vertical, particularly those regions A and B. Those regions are coincident with places of star formation. So there, what you see in the green stars, those are H2 regions. So there are vertical filaments where you have a star formation, but not necessarily having a star formation tells you that they are going to be vertical filaments. For example, W51 is one of the that you see there around galactic longitude of 50. So W51 is one of the most active main sequence star forming regions. So this is a region that is really active, is forming massive stars, and most of those stars are in the main sequence. And there we don't see a prevalence of vertical filaments. So is related to star formation, but not only to main sequence star formation. There's something else that we're missing in this case. There we also saw the purple crosses. So those purple crosses indicate either supernova remnants or H2 regions. We don't have an independent tracer of one or the other. So we think that this is related to star formation, but the answer had to wait until we had more data. And in this case, we're very lucky that there is a whole sky H1 survey, the H1/4Pi survey. So this survey was made with the Effelsberg telescope and with the Green Bank telescope in the States and in the Northern Hemisphere, and in the Southern Hemisphere with the Parkes telescope in Australia. So this gives you coverage of the whole sky. So what you're seeing there is the whole sky in H1, and in the different colors you see the Doppler shift. The fact that you see purple, green, that is a rotation of the galaxy. And there in the bottom, you see the large Magellanic, well, the Magellanic system, the large and the small Magellanic clouds. So in this case, this survey has less resolution than THOR. Remember, THOR is 40 arc seconds. Here we have 16.5 arc minutes. So it's like a factor of 10 less resolution. But in this case, we have more coverage. Since it's a whole sky survey, we can cover more of the galactic plane and do the same exercise. Just produce the filaments for the emission in different velocity channels and see how is that distributed over the sky. And this is how it looks. Okay, this is the LB diagram. Remember, this is now the whole sky. So you go from 0 degrees there in the right until 360 degrees in the left. And what you're seeing there is in the lines, I'm marking the most prevalent spiral arm structures, including 2 that have been found more recently, the outer Scutum Centaurus arm on the right-hand side, and the outer arm identified by Naomi McClure-Griffiths in 2004. So what we see, and what is very striking in this image, is just those red bands. You see very big red bands, and then you see those blue patches in that. So I'm not going to make you learn how to read an LB diagram. I don't know how to do it myself, but using the assumption of circular motions, I can produce a face-on view of the Milky Way. And this is what we have there. This is a view of the filament orientation in the galactic plane for a band of between 10 and minus 10 degrees in galactic latitude. And the take-home message in this is, do you see how all of the red is in the outer part? Is in the outer galaxy, and most of the blue is in the inner galaxy. There's a hole there in the middle that is mostly because when you have only the kinematic distance, it's hard to decide whether the objects are in the near far of the galaxy or the outer or the far side of the galaxy. So here I'm just putting all of the emission to the far side of the galaxy. The conclusion would be the same if I was doing the opposite. and is that most of the structures in the outer galaxy are very parallel to the galactic plane, and in the inner galaxy, they're mostly undecided. Many of them are vertical, some others are not. So how does this look if we average azimuthally? It looks like this. This is a radial profile of the filament orientation. So there you guys see that the filament orientation quantified by this projected Rayleigh statistic goes from mostly negative in the inner galaxy to mostly positive in the outer galaxy. That means that the filaments are oriented mostly perpendicular in the inner galaxy and mostly parallel in the outer galaxy up out to a galactocentric radius of 20 kiloparsecs, more or less, give or take. Of course, there's the position of the sun at 8 kiloparsecs, and then you see that there are some features. There's this peak around the dotted line, the dotted vertical line. That is most likely because those objects are very near to us, and it's hard to establish a global trend if they're so near, or maybe in this case, that assumption of circular motions is not valid anymore. So of course we see that feature, but the global trend is for this number to go from negative to positive and then to flatten out. That is consistent with the H1 filaments going mostly parallel to mostly perpendicular. So let's start talking about the ones that are mostly parallel to the galactic plane. Are we just seeing a rim of the galactic plane there in the outer galaxy? And the answer is no. The answer is we see filaments, we see structures, but it's not a monolith. We don't see just one filament, we see many filaments. Many of them are vertical, but the dominating trend is those mostly horizontal filaments. This is towards the second quadrant. This is towards the fourth quadrant. So you see it's a family of filaments, and the dominant trend is just that of being horizontal. Did you see this? This is the galactic warp that I was telling you about. That is also traced by the filaments. So this is the main scale height traced by the H1 emission, and this is traced only by the filaments. The fact that you see blue in one side and red in the other is the warp. That is the galactic warp. And the fact that you see red, blue, red, that is also well known. That was known before. But this is what was known before with the filaments. Actually, we see that towards the outer galaxy, when you go really outer galaxy, more than 25 kiloparsec, then that trend, that warp is a little bit changed. But you see the warp. But let's go back to this diagram. So remember, in the left-hand side is towards the galactic center, right-hand side towards the outer galaxy. So how does those filaments look? So in the inner galaxy, we have all of these vertical structures, all of those wispy things. They have been described very eloquently by Carl Heiles almost 2 decades ago. He called them worms because they look like worms that are crawling out of the galactic plane. You also see some arcs, stuff that he called chimneys, and something that could look like a bubble, but basically those are the structures that are dominating that signal, the signal that tells you that in the inner galaxy you have mostly vertical structures. Well, in the outer galaxy, you still have some vertical structures, but they're not as prevalent as in the inner galaxy. So what we're seeing is on the left-hand side, worms, and on the outer galaxy, less worms. So what is producing the worms, and what is producing those arcs that we see in the inner galaxy? The answer is related to supernova explosions. So every time that you have a supernova explosion or a family of supernova explosions, you have a phase of expansion in which you're just going to snowplow material, and you're going to accumulate it, and most of that material can be atomic. That's what we see towards many objects. Of course, this also has a kinematic imprint. You should see signatures of expansion towards the middle and less so towards the edge. But this is a process that can produce these bubbles. When those bubbles reach a scale height, when you have enough energy, so each supernova injects something like 10 to the 52 ergs, but if you have 100 supernova, you have 10 to the 54 ergs, you can produce a bubble that can be more than 200 parsecs in diameter. Then you can easily reach the scale height of the disk, so kind of the edge of the disk of the Milky Way, and those bubbles would pop. And that would leave those worms. Actually, the worms would be the walls of that cavity that has been depressurized when it reaches a scale height. Some of that hydrogen can be lifted really high. Actually, the escape velocity is really high, so most of that gas doesn't really leave the Milky Way. It rains down later, and it comes down as neutral hydrogen in what we call the galactic fountain process. So you have supernova exploding, those supernovas leave the galaxy and then rain down into the galactic potential. Of course, this is a picture from 1994. The current picture is this one. This is provided by Philip Gerihidis from University of Heidelberg, in which we see, so before I put this movie, I'm going to explain you because things are going to get bubbly in a second. So the panels here represent from left to right, the density, the temperature, the column density. So the first one is just a density slice. Then ionized hydrogen, neutral hydrogen, molecular hydrogen, and then carbon monoxide. So these are different phases that are produced in this numerical simulation. This is a 1 kiloparsec box that has a height that is more than 1 kiloparsec, evidently. And there you see 250 parsecs. So what happens when you make supernova explosions in this stratified medium, in this piece of the Milky Way? So there you see it very clearly. Every time a supernova explodes and reaches a scale height, you pop that bubble. And the remnant of that pop bubble are vertical filaments. Supernova are very efficient at lifting material off the galactic plane, and you produce cavities like the ones that you're seeing there. So what we think we're seeing is in the inner galaxy, where you're dominated by feedback, you can very efficiently lift material. If you have less and less supernova, then it's more difficult to lift that material. So does that agree with the data? Well, actually, yes. So in the inner galaxy, you have more supernova remnants, which are seen here in the gray and the green lines. So what you're seeing there are bubbles that have been identified in H1 emission with the kinematic imprint and also with the morphological imprint of these bubbles. And the further you go in the galaxy, the less supernova you see. Also, the effect of those supernova is lower in the outer galaxy because you have less and less supernova for a larger volume. That is consistent with actually the profile of a star formation rate. So also we see that the star formation rate drops by almost 2 orders of magnitude between 5 kiloparsecs and 15 kiloparsecs. So there are less and less supernova as you go into the outer galaxy. Simply you have less massive stars and less input of energy. This makes that you very efficiently lift gas off the galactic plane in the inner galaxy, but in the outer galaxy where you have less supernova, you're just dominated by the galactic potential and by the shear. What happens if you add magnetic fields? I worked for many years in magnetic fields and I made a career out of just asking what about the magnetic fields in talks? Well, in this case, the magnetic fields, they help keep those filaments coherent. The stronger the magnetic field, the more coherent are the walls of that bubble that pops. It's not that the magnetic field keeps material in the galactic plane. Magnetic fields are simply not strong enough to avoid having that bubbling, but they keep coherent the walls of those bubbles. So the stronger the magnetic field, the more coherent you see those vertical structures. So as a summary, towards the inner galaxy, most likely what we're seeing is the effect of supernova. Towards the outer galaxy, what we're seeing is just the shear motions elongating stuff along the galactic plane. So we see mostly perpendicular in the inner galaxy, mostly parallel in the outer galaxy. And this is consistent with what we know from other galaxies. Actually, this is a galaxy that by mass is pretty close to the Milky Way, NGC 6946. On the left-hand side, you're seeing just the emission in invisible light from Hubble, and on the right-hand side, you're seeing the emission in H1. This is captured with the VLA. And what you see there is that in the outer galaxy, remember that the H1 disk is much larger than the disk in stars, you're seeing those wispy structures. You see very elongated structures, which we think is what we see as horizontal filaments. But as you go into the inner galaxy, into the inner part of this galaxy, you see holes. Most likely those holes are what is left out of those popped bubbles. So what is interesting is that we think we're seeing that in our very own Milky Way, and it looks like this. Okay, I'm coming towards the end of the talk, so I'm going to tell you about what we're trying to do now. So as a small summary, we just took the observations. We found a characteristic that is giving us some insight into what are the physics that are going on, mostly feedback towards the inner galaxy, mostly shear and galactic rotation towards the outer galaxy. Something that we are trying to do is see if that orientation is inherited into the molecular clouds that we know are forming stars. These are the sites of star formation. And what we know so far is that the orientation of the filaments in H1 is not inherited by the filaments in CO. So here, what you're seeing in the right-hand side panel is just a comparison between the projected Rayleigh statistic in H1 in the x-axis and in the y-axis. What you're seeing is the orientation of the CO filament. In this particular case is 12 CO, is 13 CO, but the same is true for 12 CO. What you're seeing is that in the red part of this panel, where you have the mostly parallel to the galactic plane filaments, you have filaments in CO that are not mostly parallel to the galactic plane. And also you have some filaments in the perpendicular side. So for negative values, they're towards the blue area of this diagram, which do not necessarily have the same sign in this number, in this projected Rayleigh statistic. And you can see it very well in the left-hand side panel. This is the LB diagram. That place that looks very blue in the H1 emission actually looks red in the CO. So you're not simply inheriting the orientation of the parental atomic clouds. Something is happening in between that is perturbing that system. Of course, we know that there's feedback and there's many processes, including magnetic fields, that intervene on that. So you're not simply inheriting the orientation of the gas from the very large scales until the very small scales. There's something that is changing there. And that is the subject of our research in this project. So I came to Italy as part of the Echogal project. Echogal is a project that is a synergy grant from the ERC, led by 4 PIs in the European Union. The Italian PI is Sergio Molinari, and we are currently trying to understand those processes of inheritance from the large scales until the smaller scales where you form stars and planets. So we're working on that right now with numerical models and with other observations. And without further ado, I just announced that, of course, the future for H1 is very promising. We have the SKA, which with its imaging capabilities is going to allow us to make very, very high resolution and high coverage maps of H1. And hopefully the future is very promising for this kind of observations. So I'm just going to leave you with my conclusions, and I think I have spoken already long enough. So